Hello, I'm presenting our work. Its title is the VCU-RVI Benchmark, Evaluating Visual Inertial Odometry for Indoor Navigation Applications with an RGB-D Camera. This is a joint work with Lin Chu and Ken Yan. Visual Inertial Odometry is a robust post-estimation method that uses the data from a camera and an IMU. It is essential to many applications, including virtual reality, augmented autonomous vehicle, 3D scanning, and robot navigation. A benchmark is important to boost the development of a certain technique such as visual inertial odometry. In the literature, many benchmarks have been proposed to evaluate the performance of a VIO. The KT dataset is very famous. It is particularly for evaluating the performance of algorithm in autonomous navigation. The camera and IMU are captured at the tankers. It is enough to capture the motion of a vehicle, but maybe too slow to capture the motion of a quadrilateral or a handheld device. The Euroc dataset was proposed to evaluate the VIO performance estimating the motion of a micro aerial vehicle. However, this dataset contains limited indoor scenarios. The PEN cost VIO dataset was captured by using a handheld device, but this dataset lacks challenging conditions. Challenging here means that the device moves in conditions like undergoes the significant illumination change or surrounded by dynamic objects. The recent TOMVI dataset was also captured by a handheld device. This dataset contains various indoor scenarios, but again, it lacks challenging conditions. All these benchmarks were proposed for evaluating the monocular-based or stereo camera-based visual inertial odometry. As far as we know, there is no benchmark for evaluating the performance of an RGB-D camera-based visual inertial odometry. However, the line of the research that's fusing the RGB-D camera data with the IMU for states estimation has been applied in many applications such as 3D mapping, human pose reconstruction, ground robots, and blind navigation. Therefore, to fill this gap, we propose a new benchmark called the VCU-RVI that is particularly for evaluating the RGB-D camera-based visual inertial odometry. This dataset contains the synchronized color and depth streams as well as IMU measurements. It has 4 indoor scenarios: laboratory, corridor, hall, and stairway. The data sequence captured in the laboratory were under 3 challenging conditions, including fast motion, significant illumination change, and dynamic objects. We had 2 experimental setups, hand-holding the structure and installing the structure on a wheeled robot. And we conducted a case study to evaluate 3 VIO methods by using the benchmark as a guidance for future research. The sensor setup, the RGB-D camera we use is structural sensor. It has 2 IR camera and an RGB camera. Through stereo matching, you can obtain a dense depth image, and the dense image can be aligned with the color image by using the transformation between the stereo camera and the color camera. The IMU we used was BMI 160. The IMU measurements were captured at 100 Hz. And the motion capture system was captured at 120 Hz. Its accuracy is about 1 millimeters. We also did some calibrations, the standard color camera IMU intrinsic calibration, as well as the camera IMU extrinsic calibration by using the Calib toolbox. On top of that, we also calibrate the motion capture and IMU extrinsic by a hand-eye calibration method. In this way, we can transform the trajectory generated by the VIO into the coordinate system of the motion capture in order to evaluate its accuracy. Besides, we also did the time synchronization by a grid search approach in order to align the 2 data in the same time step. Example is showing here that the red dashed line is the results before time synchronization. The dot blue line is the result shifted by time synchronization, and the green is the result generated by the motion capture. You can see through time synchronization, the VIO results can be accurately evaluated. The data structure is showing here. The VCU-RVI data set has three parts. The first part are data sequence captured by handheld structural camera in laboratory, corridor, hallway, and stairway. In the laboratory, the data sequence was labeled as simple motion light dynamic, which I will introduce in the coming slide. The second part includes the data sequence captured by robot-mounted structural camera in the laboratory and the corridor. They are labeled as menu or bumper, which I will show you in the coming slide. The third part is called calibration, that contains some data sequences are used particularly for calibration. So here I show you some video clips labeled as lab motion. So this video can give you an intuitive idea what is its data sequence look like, what's the environment look like, and the depth data, including the RGB data. Let me first play them. These data sequences were captured by moving the structural camera at a high speed in a static environment with constant illumination. The mean and the max of the rotation speeds are about 35 and 120 degrees per second respectively. So in this data sequence, you may see that the camera is undergoing intensive rotation and translation at some point. Next, I will show you some video clips about the lab light data sequence. Again, let me first play these videos. These are data sequences captured in the case that the structure moved at a normal speed in a static environment with varying illumination. For some sequences at some timestamps, the illumination condition changes from normal indoor lightness to complete darkness. So you may see that at some timestamp, the RGB image will be totally dark at some point. At that moment, you can also see the depth image will not be affected by the changing illumination. For example, you can see here at this point, the color image is totally dark. So next time we show you some data sequences that labeled as dynamic. Again, let me first play these videos. So these data sequences are captured in the case that the structural camera moved at a normal speed in a dynamic environment with constant illumination. The dynamic objects may include 1 to 2 persons, a chair, a wheeled robot, or a rollator. You may see that this is a man is pushing the rollator here. This is he's doing the bumping jump. And this is a moving objects, moving robot with a person. Okay, this is a video that's showing that is captured in the corridor and hall scenarios. It is speed up by 5 times. So you may see that the camera is moving in the scenario that in the hallway, maybe sometimes in the stairway and around the hall. So this I'll show you some videos of the data sequences captured by robot-mounted structural. The first row showing the data captured in the laboratory, the bottom row showing the data captured in the corridor, and they are played speed up by 5 times. And the first column is data sequence labeled as menu. The second labeled as bumper. In the menu case, we first hand holding and rotating the structural camera for about 5 seconds to produce sufficient IMU excitement for a good system initialization purpose, and then placing the structural camera on the robot and driving it to move. In the bumper case, we first driving the robot to move across the bumper to produce sufficient variation in IMU measurements for initialization, and then driving the robot around in the whole area. We also conducted some case studies. We implemented 3 visual inertial odometry methods by using the benchmark. The first is the Wins model, second is the Wins RGB-D, third DU-RVIO. The last 2 methods are RGB-D camera-based VIO methods. The last one is our proposed method. This figure showing some qualitative results, and the trajectory generated by these 3 methods are plotted and compared with the ground truth. You can see it for different data sequence labeled here. Also, I'll show you some quantitative results. This is all the data sequence captured by hand holding the structural camera, and the absolute pose error are showing in this table. The best results are black folded in each row. Similarly, this is the results with the data sequence captured by the robot. The absolute post error are showing in this table for these 3 methods. So concluding, we present VCU-RVI benchmark to evaluate the VIO methods for indoor navigation applications. The dataset can be used to test a monocular or RGB-D camera-based VIO methods. All data sequences, the evaluation tools, algorithms are made publicly available. You can access them in the bottom link. Okay, thank you for your attention.